Hello, in this video I'm going to keep talking about stars. So we've already gone through how stars got their names, how we locate them in the sky, looking at the equatorial coordinate system using declination and right ascension that locates stars on the celestial sphere. So we got all of that, but next thing we want to know is what they're made of, how they're structured. And then we can think later on about talking about their life cycle, how the stars actually evolved. But in this video, I'm going to be talking about what they're made of, how they're structured, at least at a sort of basic level that we can flesh out in later videos. Right, and these are relatively recent discoveries. People have obviously known about stars since the dawn of time. You go outside and you can see them in the night sky. But it's only in the last couple of hundred years that anyone's really known what they're made of and how they're structured. So the main jumps forward being early 19th century with Joseph von Fraunhofer setting up spectroscopy. So spectroscopy, this is looking at the spectrum of a star, which I'll talk about more in later videos. And that allows us to work out what stars are made of. Now, it wasn't immediately apparent when he developed spectroscopy exactly what we were looking at. You could point your spectroscope at the sun and get some information, but this was the start with Fraunhofer, the start of about 100-year path all the way through to the 1920s, when Cecilia Payne-Gaposchkin then correctly asserted that the sun is mostly made of hydrogen and helium. So it took a good century to work out that that was the state of affairs. And that's only about 100 years ago. So this is relatively recent stuff. Obviously, we've come on leaps and bounds since then. But yeah, it's not anywhere near as ancient as the other parts of astronomy. So what we do know is that stars are balls of plasma. So this is something new to us. Or at least we would have heard the word, but probably don't know an enormous amount about plasma because we don't talk about it much before we head off to university. It's the fourth state of matter, and it only occurs and is sustained in very high energy hot situations. So this is why we're not that familiar with it. It doesn't exist in everyday life in the way that solids, liquids and gases do. We encounter them on Earth in, say, lightning, or if we actually construct them in a plasma screen or something like that. But it's not something we come across on a day-to-day basis. And a plasma is a highly ionized substance, so not necessarily 100% ionized, but the electrons are mostly separated then from the nuclei. We don't have atoms with filled up shells of electrons around them. The electrons have been ionized out. So we've got positively charged nuclei, we've got our negative electrons, and there's enough ionization that it becomes a plasma. It's so highly electrically conductive that its behavior becomes dominated by electromagnetic fields. So this is very different to just saying, oh, we've got an ionized gas. Don't think of plasma as being equivalent to something we did in thermodynamics with ideal gases. These aren't just ionized particles. They're not just charged particles bouncing around with these sort of billiard ball collisions that we were talking about in ideal gases. This is a very different setup. Each particle is behaving in a way that depends upon its electric charge and its mass, and how that reacts inside the electromagnetic field. And of course, we've got the movement of those charged particles in the plasma is generating an electromagnetic field. So you've got this continual feedback between the motion of the particles, the creation of the electromagnetic field, and then that affecting the motion of the same particle. So it's a very complicated setup, and that's why plasma physics is a branch of physics in its own right. So that's what stars are made of, though. You've got this plasma, big ball of plasma. And then in terms of the structure, well, let's get a rough idea of structure down. We'll talk about the structure in more detail when we get onto the life cycle of stars. But let's take an example then of the sun. Seems like a reasonable star to pick, just to get a basic idea of structure. And it's a fairly average star. It's when you look at the outside, because you've got the issue of, well, you can only see what you're looking at, and this is a picture here of the sort of granular pattern that you get on the surface of the sun. If you look at it through a solar telescope, you'll see all these little granular sort of blobs all over the surface. Now we can only see what's on the outside of the sun, and looking at the outside, it looks as though it's about maybe 75% hydrogen, 25% helium, that sort of split, that 3-to-1 split, hydrogen to helium. But in the middle, there's a lot more helium. You might have 60% helium in the core, and heavier elements. And in astronomy, when we say heavier elements, we mean anything that's heavier than helium. So it doesn't have to be that heavy. They sink inwards because of the effect of gravity in towards the core. So you're going to get less hydrogen as a percentage in the core compared to the heavier elements. It's going to drop. The percentage of hydrogen is going to drop as you move in towards the core. And I'll come back to this granular pattern at the end. So talking about the core then, so that's the central part of a star. This is where the fusion is going on. So we've got nuclear fusion going on inside the core. This might be about 25% of the radius of the sun, up to about 25%. It's going to vary depending on where a star is in its evolution. You're looking at something like 15 million Kelvin. It's hot there. We were looking at this in nuclear physics. If you're going to have nuclear fusion, you need to be getting up to these really high temperatures so you can get positively charged, essentially protons and other positively charged nuclei in some cases, close enough together for the strong nuclear force to take effect and fuse those protons together. So it has to be really, really hot. It's really dense. You're looking at around 150 times the density of water in the core. And this is where all the fusion happens. Now, mostly this is happening through something called the proton-proton chain, which converts hydrogen to helium. But there's also a little bit of what's called the CNO cycle going on. So we've got the proton-proton chain and the CNO cycle. Now, don't worry too much about those at the moment. I'm going to do a separate video on fusion in stars, where I'll talk about both of those. Now, in stars the size of the sun, it's mostly proton-proton chain. You get CNO cycle in heavier, more massive stars is where you get more of the CNO cycle. And you've got an enormous amount of fusion going on. You're looking at around about 4 times 10 to the 38 protons per second are being converted into alpha particles. Now, of course, when we're saying protons, really, I mean, this is the hydrogen that's being fused into helium. We've got a plasma, so it's ionized. When we're talking about hydrogen, we're talking about protons because it's ionized hydrogen. And that is what's being converted then into helium. And we're getting an energy release because of that. Protons on their own don't have binding energy. And then you bind them together into helium. And because they're more tightly bound, you then have to get an energy release. So again, I spoke about all of this in nuclear physics. So if you're not, if you've forgotten your binding energy or you haven't come across binding energy yet, then go and watch the videos on nuclear physics. So we've got this every second. So that's our per second. So that's an enormous number of protons that are being converted into helium every second. So that's where our energy is being produced. And this is getting released in kinetic energy of the fusion products. It's getting released in photons. And this ends up being the key feature in terms of the evolution of stars, that you've got energy being released outwards and you've got gravity pulling things inwards. And when we get on to looking at the life cycle of stars, it's that that sort of balance or conflict between energy pushing outwards and gravity pulling inwards that determines the phases in the life of a star, which again I'll talk about in another video. Right, outside the core, you get the radiative zone. So radiative zone, and as the name suggests, this is where energy transfer is by radiation. So you've got photons moving around. So this is taking us from 25% to say 70% of the radius. And it's getting cooler. You know, we're dropping down from, we might be at about 7 million Kelvin down to say 2 million Kelvin as a temperature change going through the radiative zone. And when you get to the end of the radiative zone and we move into then a change in how the energy is transferred as we move into this convective zone, well, between these there's a change in the rotation of the sun. So the core and the radiative zone, they have a fairly uniform rotation. They rotate like a solid body. When you get to the end of the radiative zone and then moving into the convective zone, it changes. You start getting non-uniform motion. And it's believed that this change in what's referred to as the tachocline, is key to the formation of the magnetic field of the sun. But the magnetic field of the sun is not that well understood. There are a lot of questions over how that is formed and how it operates and how it transfers energy around. But anyway, so you get that change. You then move to the convective zone. This then takes us from the 70% radius up to pretty much the surface. So just below the surface. And we're now getting bulk transfer of matter, which is moving the energy from deep inside the sun out towards the surface. So, and this is starting to set up because the density is dropping as we're moving out from the core. The density is reducing. When the density gets low enough, convection currents can then form. So you'll get this change in density. You've got a hot bit of material that's got the lower density. It rises up, it cools, it gets higher density, and then it drops back down again. It's the same convection process that we see, well, anywhere really. We're familiar with this on the Earth. But yeah, the usual thing, it rises, it cools, it increases in density, and then it sinks again. And it's these convective currents that cause this granular effect. Essentially, these are columns going into the sun. So each one of these little cells that you're seeing here is like the top of a column of convective energy transfer. So that's why we've got that effect there. Right at the top, so when we get to the surface is what we refer to as the photosphere, and it's called photosphere. This is where the photons come out. When the photons, which are making their way out of the sun, these ones that have been produced in the core, they're working their way through the radiative zone, then you've got transfer of material in the convective zone. When they get to the photosphere, photons in the photosphere can escape from the sun. So that's the bit that we're actually looking at when we observe the sun. That's where the photons are coming from. So any observation that we're making with a solar telescope is telling us stuff about the photosphere. So the temperature here has dropped down, surface temperature of the sun, 5,700 Kelvin, thereabouts. Density has dropped down massively. So yeah, things have become much thinner in the photosphere, and that's why these photons can get out. Now, beyond to the photosphere, the sun does have an atmosphere, and the atmosphere is, first of all, you've got the chromosphere, and the chromosphere, things start heating up again. Okay, it might drop down to say 4,000 Kelvin, but you might get up to 20,000 Kelvin, something like that. So it's getting hot in the chromosphere, but not as hot as then the corona. Now, the corona you may well have heard of. It gets ridiculously hot in the corona again. So it's got an average temperature of maybe 1 to 2 million Kelvin. That's average. You can get temperatures up to say 20 million Kelvin in the corona. It is the hottest part of the sun, and there's some mystery around all of this. It's connected to the sun's magnetic field. It's an unsolved problem. There isn't a definitive model at the moment of how so much energy is reaching parts of the corona. And we see the atmosphere of the sun, and we see the corona when you get a solar eclipse. You know, we're used to seeing the black disk with all the sort of, you know, whatever wafting around the outside. That's the corona that we're looking at. And it's quite bright because it's so hot. Even though it's really thin, there's a lot of energy just coming out of it when you block out the actual disk of the sun. So that's the corona. Beyond the corona, you then start getting into the solar wind. So you've got what's called the heliosphere, running out of space here, but the heliosphere, and this extends right out through the solar system. You've got the solar wind. This is charged particles which are flowing away from the sun through the solar system, all the way out to what's called the heliopause, where the heliosphere stops, essentially. That's the edge of the solar system. You're going out to about 50 astronomical units, so 50 times the distance from the sun to the earth. That's getting to, you know, the heliopause and what we consider the edge of the solar system. You know, so 50 astronomical units as a comparison. Neptune, the outermost planet, is at 30. So from 30 astronomical units, you've got another 20 to go until you hit the edge of the heliosphere. So yeah, it extends out. You know, as with these things with atmospheres, you know, where does an atmosphere end and space begin? You know, it's not an easy thing to say, right, well, there's the definite dividing line between one and the other. So that's why you've got this this idea of a heliosphere and how the atmosphere of the sun is really extending all the way through the solar system. Right, so that's a whistle-stop run-through of the structure of a regular-looking star. You know, the sun is not particularly distinctive or unique in any way. There's loads of stars like the sun around. It's not particularly big. It's not particularly small. It's a pretty average star. So it's a good starting point for talking about the structure. What we need to do now is go back to this spectroscopy, see how spectroscopy works, and then that will allow us to understand how to classify different stars, work out the different types of stars. How do we spot a really big hot star as opposed to a smaller, cooler star? You know, what sort of stars are there out there? How are they constructed? What are they made of? And then how do they end up being made in the way that they are? So without that that understanding of spectroscopy and how to classify stars, we can't really understand the life cycle of stars. So we have to do that bit first. Once we understand that, stellar classification, we can then do stellar evolution. So that's what I'm going to start moving into in the next few videos.